first speaker this afternoon is Takeshi Matsumoto from Kyoto University, and I look forward to learning how vorticity aligns in isotropic turbulence.
Thank you. And I thank the organizers to give me the opportunity to talk about our ongoing work with course Professor Kimura is sitting there. So this is about single fluid, inactive, but still there's a alignment, and I start slowly. And if you have questions, please don't hesitate to ask me any questions. Okay, so this is so-called homogeneous isotropic turbulence, which was talked about by Druba before lunch. So this is some animation of the velocity field. So these small things are actually vectors, and those green thing is iso surface of the squared vorticity. So it evolves in time and it's random. And so this is a simulation of the Navier-Stokes equation, and forcing is added in a large scale, and it is incompressible. It's maybe the simplest way to achieve the turbulent flow. So if we start this simulation with the forcing in a large scale, added in the forcing, so it reaches in a statistically steady state, and the statistics of the velocity field or vorticity field becomes homogeneous in space and isotropic. So that is what we call the homogeneous isotropic turbulence. So this is maybe well-known phenomena, and so we know the velocity increments or some statistics of the velocity obeys universal scaling laws. The most representative one is, I forgot to put some equal sign here. So the energy spectrum goes like wave number to the power minus 5/3. So this is famous universal scaling laws. But today I talked about very different laws or order in turbulent flow. So that is what we call, what is called vorticity alignment, found in 1987 by those authors. And this is quite fascinating phenomena. So this means the vorticity vector, pointwise, tends to align with a certain direction. So I will explain what the certain direction means. Okay, so this is a vorticity equation. So I added the forcing. So this is coming from the large-scale forcing I wrote for the velocity field. And so here's a rate of strain tensor. I write as S. So Sij is a symmetric part of the velocity gradient tensor. And in terms of this rate of strain tensor, the vorticity equation, in particular the stretching term, can be written in this way. It's very simple. So there's rate of strain times the vorticity. And so this S, the tensor S, is symmetric at each point, at each time. So that can be diagonalized pointwise and instantaneously. But let me denote those eigenvalues as lambda 1, lambda 2, and lambda 3. And because we have dealing with incompressible flow, the trace of rate of strain tensor S is 0. So that means the summation over this lambda j is 0. So this is the basic fluid dynamics. And so S can be diagonalized. So S has eigenvalues associated with each eigenvalues. So let me denote the largest eigenvalue of the rate of strain tensor with the lambda 1, and the smallest is lambda 3. Because the sum is always 0 because of the incompressibility, so lambda 1 is generally positive, and the smallest eigenvalue is generally negative. And okay, so the eigenvectors associated with lambda 1, here I wrote this E1, and E2 is the eigenvector associated with the lambda 2, intermediate eigenvalue. And the E3, vector E3, is the eigenvector associated with the smallest eigenvalue of the rate of strain tensor. So this is nothing but the introducing the principal axis of the rate of strain tensor. So, okay, now I can state the vorticity alignment more specifically. So the vorticity at some space point and some instantaneous time, the vorticity vector tend to align with E2. So this is the eigendirection of the intermediate eigenvalues. So this was found in 1987. And so this is really subtle and sounds very fascinating. So let me go back to the original paper by Ashurst. And they showed this kind of probability of the cosine. This theta I is the angle between the eigendirection EI, between the eigendirection EI and the vorticity vector. So as you can see, there are three curves. So this is the most interesting thing. So beta is in their notation, so beta corresponds to E2 in our notation. So this is the PDF, not exactly PDF, they say probability. The probability of cosine theta 2 becomes large for the cosine is 1. So that means theta 2 equals 0 is most probable. So from this observation, they say the vorticity, omega, tend to align with the eigendirection of the intermediate eigenvalues. So this is the vorticity alignment, which we study in this talk. So this is 1987. So the Reynolds number based on the Taylor microscale is 83. I think this was the cutting edge simulation at the time. So now we can go much larger Reynolds number. So this is a state-of-the-art simulation, I believe, by Navier-Stokes 2020. So the Reynolds number based on the Taylor microscale is 1300. So basically, the PDF of the cosine is the same. So we have a peak at the cosine theta 2. So this is the EI is the same as our notation. So the vorticity tend to align with the eigendirection of the intermediate eigenvalue. So that is true also for the much higher Reynolds number. So those PDFs probably do not depend much on the Reynolds number. So that's good news because we can study those alignment property with smaller simulations. Okay. So the vorticity alignment is found, and there are several remarks. So this is a spontaneous orientational order in the homogeneous isotropic. Yeah, homogeneous and isotropic is in a statistical sense. And also this vorticity alignment is a statistical sense. But this is a spontaneous orientation order. And here's a remark by a review paper by Schumacher and Horiuchi, written in 2013. So they say this vorticity alignment was considered unexpected for the statistical physics community. And, but this alignment has been anticipated by the vortex dynamicists, such as Tenekes and Lundgren. And there are nice models of vortex stretching and how the vortex is amplified. So given those models, some fluid dynamicists consider this alignment is as expected. So this is a very interesting remark, and I can tell you, sometimes I talked about this vorticity alignment with my colleague doing the statistical mechanics. Quite often, they are really surprised why such kind of alignment exists in the homogeneous isotropic turbulent flow. Vorticity should be always random. This kind of order is really hard to understand intuitively. So anyway, so this is I think this is a very nice remark. And the vorticity alignment means also another fact is so we can write an equation for the magnitude, squared magnitude of the vorticity. So we have this term, and this term is responsible for the amplification of the vorticity magnitude. And this alignment with the intermediate eigendirection means this term is not completely effective if the vorticity is always aligned with the largest eigenvalue direction, then the stretching occurs most efficiently. But this alignment tells you this term is actually very subtle and not maximally working. So in this sense, it's really interesting, and the vorticity alignment can be considered as the depletion of the nonlinearity. Okay, so then the question, so why this preferential alignment of the vorticity occurs? And that has not been answered. So this is actually the statement made in their review paper. So why the alignment dominates has not been answered. And it was made in 2013, and I think this is still true. And okay, so now we are addressing this question. So the first, so we revisit alignment with some coordinate spanned by the eigendirection of the strain. So this is the natural thing you can do with simulation data. So the second part is we develop a model. And so this model is a simplification of the direction between the vorticity and each eigendirection of the vorticity. And then we can analyze this dynamical system model with the computer and also do some simple analysis. And the last part is very different from the part 2. And we use this coordinate to extract typical vortical structure or strain structure, which is considered to be responsible for the alignment. So this is the 3 parts of my talk. So I will start with the revisiting alignment with local coordinates. Okay, so sorry, this is a handwritten here. And so this is the local strain coordinates. So here is the x prime axis. This x prime axis corresponds to the E1, the eigendirection of the largest eigenvalue. So the z prime, so I said z prime axis is the direction of the eigenvector of this intermediate eigenvalue. So this is E2 basically. So then E3 is the eigendirection for the minimum eigenvalue. Then, so here's our vorticity. And I just use the simple spherical coordinates, the azimuthal angle phi and the polar angle theta. So this is very natural thing you can do. So just to remind you, so we have a rate of strain tensor. There are 3 real eigenvalues, and the lambda 1 is the largest, lambda 3 is the smallest. And because of this trace is 0, so lambda 1 is generally positive, lambda 3 is generally negative. So E1 corresponds to the x prime axis, E2 is z prime, E3 corresponds to y prime. So the vorticity can be written in this spherical coordinates. It's as very simple. So here's lambda is the magnitude of the vorticity vector, theta is the polar angle, phi is the azimuthal angle. And without loss of generality, we can set this polar angle is in between 0 and pi over 2, and the azimuthal angle existing between minus pi over 2 to pi over 2. So the next natural thing we can do is to calculate the frequency of the vorticity, which polar angles are preferred by the vorticity field in the homogeneous isotropic turbulent flow. So I have used the same data and calculate the PDF. So this is the result. So this is a x prime, y prime, z prime. So this is a polar angle, and this is a azimuthal angle. So the color corresponds to the probability density function of the vorticity vector, orientation of the vorticity vector. So you can see there's some maybe not very sharp, but here's a peak of the PDF. And you can also see the PDF is symmetric with respect to x prime axis. And okay, so our simulation is not really very cutting-edge simulation, so the Reynolds number is about 200. So that corresponds to 500 cube simulation.
Is this a snapshot or time average?
Okay, so it's averaged.
Average.
Yes, averaged.
And you have stationary turbulence.
Yes. Okay, so I just expand this PDF in the plane of theta and phi. So the theta is the polar angle, and phi is the attribution angle. So the peak is located around here, and if we measure the numbers of this coordinate, so the coordinate is roughly corresponds to 0.035 pi and 0. So maybe this exact number may depend on the Reynolds number, but for the Reynolds number 200, so the theta star is the peak location of the peak is maybe not 0, but it's a very small value. Okay, so then let me observe the shape of the PDF. So it's symmetric with respect to this axis, and the peak exists in these numbers, and which is a small angle, but maybe not 0. And what this means is, okay, so on average, the vorticity vector doesn't have a component on this y prime axis, on average. And the peak polar angle may not be 0, or it may go to 0 as we increase the Reynolds number. So that's, we are not sure. But for the finite Reynolds number, it may be non-zero. Okay, so this is the first part. So, yes?
Precisely what sort of forcing do you use?
Okay, so it's a large scale, and the forcing is proportional to the velocity field. So sometimes it's called a negative viscosity.
You think that this PDF does not depend on the type of forcing?
Okay, so the answer we don't know, but those vorticities and the strains are small scale phenomenon. So in that sense, forcing dependence may not be not very strong. Okay, so now we are going to the part 2. So we have introduced some spherical coordinates, and we use the same spherical coordinates and try to develop a model for those alignment. Basically, the vorticity can be written in this coordinate, and we assume the vorticity does, sorry, so this is z prime corresponds to the E2. So this is z prime component is omega times cosine, and x prime component can be written here. So we assume the y prime component is 0 from the knowledge of the shape of the PDF. So we assume this thing, and we try to model the evolution of magnitude of vorticity and the angle as a function of time.
Sorry,
yes.
Everything's a function of position as well.
Yes, 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 yes. It's but we assume from now on we follow the Lagrangian evolution, and since the flow is homogeneous, and we basically pretend to neglect the spatial dependence. So the
Good afternoon.
yes. Okay, so from this representation, the tangent of the angle between the vorticity and the eigendirection of the intermediate eigenvalue can be expressed in this manner. So then, yeah, what we want to do is a model of the evolution of the omega t and E1 and E2. Then we can have the evolution equation of the theta. So this is a result. I will show you how to derive it. But anyway, so this is the equation for the theta, and this omega is the magnitude of vorticity, and lambda 1, lambda 2, lambda 3 is the eigenvalues of the rate of strain tensor. So yeah, the method we developed this model is basically it's the same as the old model of the BA-FOSS published in 1982. But maybe the main difference or subtle difference is this one, the equation for the angle. And just to remind you, we assume the azimuthal angle of the vorticity is 0. We restrict ourselves in this situation. And in deriving this model, we ignore the viscosity and forcing. I will talk about in a minute. Okay, so again, sorry for this handwriting thing. So this is the equations we use to develop the model. So this is a vorticity equation, and this is the equation for the rate of strain tensor in the Eulerian coordinates. So this is the tensor product of the pressure, or the pressure Hessian, and the third one is the equation for the pressure. So there are 3 sets of equations, and we pretend everything is evolving in a Lagrangian frame. So at time t, we have this local coordinates. Local meaning the coordinates depends on the Eulerian coordinate x. Then after time t plus dt, so this point is affected to this point, and of course these eigen-direction changes and the vorticity directions of changes, and we like to model those evolutions. So we ignore the viscosity, and then we pretend to be in the Lagrangian coordinates. So this part is just the omega dot, and this part can be s dot, and the rest is this one. So we like to model those terms then. Okay, so the evolution of the vorticity is very simple because it can be written as a product of the rate of strain tensor times the vorticity, and the rate of strain tensor in this coordinate is diagonalized, so it's very simple. And we assume the vorticity doesn't have a y prime component, so it's very, very simple. And from this equation, we can write the vorticity at time t plus delta t, and this can be just very simple. So we just use this one, and up to the first order of delta t, we have this thing. So from this expression, we have the evolution equation for the magnitude of the vorticity vector. So it's very simple. Okay. So the next thing is the evolution of the rate of strain tensor, or the evolution of the eigenvalues. So this is the equation for the rate of strain. We are in the Lagrangian coordinate. We ignored viscous contribution. So this capital omega is the antisymmetric part of the velocity gradient. So this can be written in terms of the vorticity components, and since we have expressed the vorticity in terms of this local strain coordinate, and those components can be written in this way. So it's again very simple. The big problem is this part, the pressure Hessian. We don't know how to write it in terms of the omega or theta or lambda 1, lambda 2. But the only hint we have is the equation for the pressure. So this equation for the pressure, so that can be written as Sij squared, and also the magnitude of the vorticity. So this is basically the trace of the Hessian. So maybe the simplest modeling is the pressure Hessian is identity matrix. So everything is isotropic. We assume everything is isotropic, and this part is coming from 1/3 of the trace. So this is maybe the most simple model, and you can criticize actually, and it may be hard to defend. But theoretically, I think this is the first thing you can do. You can try. Okay, so then we have every terms are expressed with lambda 1, lambda 2, lambda 3, and omega and theta. So then we plug those expressions into the evolution of the strain. Then we have this kind of expression for the rate of strain at t plus delta t. So the rest is to solve the eigenvalues and eigendirections of this 3 by 3 matrix. So it's 3 by 3 matrix. So it's, in principle, everything can be computed. So the largest eigenvalue can be expressed in this manner. So this A and C are given in this manner, and the corresponding eigenvectors can be written in this way. So then, okay, sorry. So the second largest eigenvalues can be just a minus sign, and the corresponding eigenvectors can be written in this way. And the smallest one is this thing, and the smallest one is very peculiar because of we assume the vorticity doesn't have a y prime component, and the consequence of that thing is this thing. So the eigenvector for the smallest eigenvalue is quite simple. So with combining all those results, we arrive at.
Sorry, what's that?
Yes.
E3 of t plus delta t. What's that double slash symbol? I'm sorry.
Oh, sorry. This is parallel.
Ah, that's
Sorry. Parallel.
Okay.
Parallel. Parallel. Sorry. This is parallel.
Sure. Oh, excuse me.
So then we just expand things in the delta t up to order 1. Then we can arrive at those evolution equations. Lambda 1, lambda 2, lambda 3. And as you can see, if we add those equations, the right-hand side is 0. So that means trace is conserved. And the evolution of the angle is the one we want to have. So we have those, we plug into every equation here. Then we have this evolution of the angle, polar angle, in terms of the tangent. But that can be written in this manner. So then we arrive at the equation for the polar angle. So we assume lambda 1 is always larger than lambda 2. So here we decided not to worry too much about those denominator becomes 0 situation. Okay, so this is the model we have arrived at. So the lambda 3 is given by the minus lambda 1 and minus lambda 2. So we pretend to follow everything in the Lagrangian coordinates. And we assume the azimuthal angle of the vorticity is always 0. We restrict ourselves in that situation because that makes things simpler. And the third one is we ignore viscosity and forcing. And then the last one is maybe the biggest assumption. Pressure Hessian was modeled isotropic form. So it's proportional to the identity matrix. So anyway, so we have this kind of nonlinear dynamical system. And we can solve it numerically, or we can analyze the right-hand side to find the fixed point. Okay, the first thing I will show you is a numerical simulation. So this is a model. So the initial values for the lambda 1, lambda 2, omega, and theta can be taken from DNS data. We just look at the grid data of the direct numerical simulation of the turbulent flow, and choosing the grid points where the azimuthal angle is very small. Then we put the lambda 1 value, lambda 2 value, and omega values into this equation as an initial data. Then we solve this dynamical system. So there are 8 trajectories I plotted here. So the one trajectory is going down and 0 becomes 0. And they actually, at this point of time, the eigenvalues and vorticities becomes infinite. And there are other trajectories starting from here is going this way. And here, again, the vorticity and the lambda 1 diverges. And the one typical behavior is shown in this trajectory or this one. So it stays not exactly 0, but some small polar angle. And it stays so for a long time. So this time is normalized by the large scale turnover time. So that means this plateau has some order of the large-scale turnover time. And after that, yeah, this equation seems to diverge. So, but we concentrate on this behavior or plateau of the polar angle at small value corresponds to the vorticity alignment. Okay, so I took one trajectory as an example, and this is a model, and it can be shown. This is very simple. So this right-hand side vanishes when the theta is 0, omega is 2 lambda 1, and lambda 2 equals 0. And there's no other interesting equilibrium point for the theta equal pi over 2. So this theta equals 0 is perfect alignment with E2, the eigendirection of the intermediate eigenvalues. So this theta equals pi over 2 corresponds to the alignment with the largest eigendirection. So this is the result of the model. And okay, so this numerical result of the model, and it shows a plateau, and we like to understand this plateau is a kind of flyby or of the equilibrium point, or meandering around this equilibrium point. So this is a check. So this is the same plateau trajectory. So here I plot the omega, lambda 1, and lambda 2. So this is a condition of the fixed point. So theta is around 0. That is okay. So the omega should be 2 lambda 1 for the exact fixed point. So lambda is here is about 24. So here lambda 1 is maybe 11 or something like that. So that means this condition is satisfied roughly. And lambda 2 is much smaller than lambda 1, and it crosses 0 around here. So that means the equilibrium condition is roughly held during this plateau. So that means this plateau corresponds to a flyby, the equilibrium point, and that may correspond to the actual preferential alignment of the vorticity in the homogeneous isotropic turbulence. Okay, so here's the summary of the model. So this is a model we considered. The polar angle theta equals 0 corresponds to the perfect alignment with the intermediate eigendirection of the intermediate eigenvalue. And this model tells us there's a fixed point, and the numerical solution, some numerical solution, shows some long transient states around this fixed point. And okay, so from this result, we like to consider the actual preferential vorticity alignment in the homogeneous isotropic turbulent flow may correspond to the same kind of flyby. So I like to check. Yeah, we like to check this statement. So maybe the simplest thing is to look at the scatter plot. So this is data from the numerical simulation of the Navier-Stokes equation. So the horizontal axis is lambda 1, and the vertical axis is the magnitude of the vorticity vector. So, but here I took the grid data where you have near alignment to the E2. So that means azimuthal angle is basically 0, and the polar angle is 0. So it's close to the Z prime axis. So I just took the nearly alignment data and the scattered plot. So this, yeah, there are two lines, and this lower line corresponds to omega equals 2 lambda 1. So the best fit, so I have used the least square fit with those scatter plot. So that least square fit gives you the number 2.23. So this one is not very different from 2. So that means though this equilibrium condition, this equilibrium condition may carry over to the real turbulent flow. then we can plot in the 3D space and lambda 1, lambda 2, and omega space by taking the data from the direct numerical simulation. And then we can also do the least square fitting, and this least square fitting in the 3D space gives you this number. And this number is not far away from the equilibrium condition. So that means the insight from the model probably is useful to understand the real preferential alignment of the vorticity in the homogeneous isotropic turbulence. Okay, so these purple points are data which shows alignment with E2. The green dots are taken from all the grid points. So for the grid point data showing alignment is close to the equilibrium condition, but in general they are scattered everywhere, and large vorticity data is probably quite different from the alignment property here and there. Okay, so this is the comparison between the model and the simulation of the Navier-Stokes homogeneous isotropic turbulence. Okay, so we have done with the model, and now we are moving to the other use of the local strain coordinates. So it's different from the development of the model. So here we like to understand not the model, but using the simulation data and taking, there may be some typical structure which is responsible for the alignment property. And the idea is to extract if those typical structure exist, and that can be extract by taking the average. So this is the idea. So the question is, there may be some structures, vortical structures, strain structure, streamlines, responsible for the preferential alignment vorticity. So we often talked about in turbulent flow, vorticity can take the form of sheet or tube, and that kind of question. And the strain field, so we typically consider the strain field is hyperbolic or elliptic and so on. And then the second question is, can we extract such structures? If exist, how one can extract those structures? And maybe there are many ways. There are many ways to define the so-called coherent structures, but here we stick to very simple-minded averaging. And the simple averaging from the, so you have the domain of the simulation and take the subdomain and just simple taking the arithmetic average, then everything goes to 0. But if use the local strain coordinates, and also always we take the z prime, y prime, x prime in the same direction and take the average, then what we'll get? Maybe the vorticity alignment property will give you some non-trivial structure of the vorticity and strain field. And this is an idea. Okay, so this is the whole your simulation domain. So if you take this point, the local strain coordinates looks like this, and the other points, the z prime coordinates is this one, x prime this one, y prime this one. And the other points, those local coordinates pointing completely different direction. But we take this subdomain and rotate, and we take this subdomain and rotate, and always z prime is the same direction, x prime is the same direction. And then we take the average over these rotated data. Then what we'll get? So this is the vortical structure. This is an integral curve of the averaged vorticity vector. So this cube is basically the subdomain, and the side length of subdomain is 64 eta. And this averaged vorticity line has some tilted angle. This z axis is the same as the z prime we talked about. So those averages over the rotated subdomain gives us something. And so at the center of the subcube, or average data, have some tilted angle, and that corresponds, okay, sorry, so this subdomain average, I didn't put any condition. I took those non-overlapping subdomains in the simulation field and take just the stupid arithmetic average of the rotated subdomain. Then this is what we get. So the side length 64 eta is worth commenting. So this 64 eta is half of the side length is 32. 32 eta is found by Hamilton et al. Is responsible for the preferential alignment. And if we consider the far field far away than 32 eta, that doesn't change the alignment property. So this is found by these authors. So that gives that that kind of knowledge is used in this subdomain averages. Okay, right. So this is the vorticity line around the x prime z prime plane. Here is the top view of this average subcube, and this blue thing is the isosurface of the vorticity. And you see big pancake, and also here is two horizontal structure, and this is a side view. So this is this main structure, and there are two satellite vorticity, and that indicates there are some typical structure, but we still don't know this is really responsible for the alignment property. But from the average of the rotated subdomain, we see something, and so this is the slice of the middle plane. So the color shows you the z prime component of the averaged vorticity, and those lines are average streamlines. So that means, yeah, that tells you those rather beautiful but not simple structure. So we have plus vorticity, z prime direction plus vorticity here and there. And here we have weaker negative vorticity. That corresponds to the satellite vortical structure. And yeah, from this color plot, we can imagine there are some kind of quadruple exist in this averaged vorticity. And this quadruple may be responsible for the alignment. Okay, so this is a bit quite different averaging. So we here condition the magnitude of the vorticity is larger than 5 sigma. Sigma is the standard deviation of the vorticity magnitude distribution. So this corresponds to the very high vorticity region, and we took those high vorticity region and take the same average. So this color is again the z prime component of the vorticity. So you see this is not really spherical. It's somewhat deformed spherical, and this direction is 45 degrees between x prime and y prime, and the average streamline is here. So this structure is different from the previous one. So that means the high vorticity region has a different structure, and if we can understand these structures and strain field, then maybe we can understand extreme events. And these figures is very much reminiscent of the biaxially strained vortex discussed in the Moffat-Kidao-Kitani in 1994. And this is conjectured to be not exactly stationary, but the lifetime of those kind of biaxially strained. And this samples shows this is, though they are lambda 1, lambda 2 are always positive. So that corresponds to the biaxially strained vortices. And maybe we have some nice understanding of those extreme vortices. Okay, so this is the end of my talk and summary of the talk. And thank you for your attention.
Can you show me the picture at the very beginning of your lecture, the figure in which you said that there is alignment and there's a peak at 1?
Yes, cosine. This thing?
Yes.
Yes.
So the peak is at 1, but the probability to be at 1 is rather small.
Yes, so yes, the peak structure is not
Peak is at
the...
1, yes, but the integral is like less than 1, it's much larger. The probability is the integral.
Mhm.
So yes, you have a mode peak at 1, but nonetheless the probability to be at 1 is very small.
Yes, I agree,
So
Actually, this is not...
What's the indication that indeed there is alignment?
Right. So that's
Probability
why...
of being aligned is very small.
Yes, so that's why we calculate this thing. So yes, but the yes, integral is matters, and right, yes. So yes, you're right. Yes. Actually, the real grid points showing the alignment may not be really dominating. Actually, I agree with this. Please.
Yeah, if I understood correctly, your model was very close to the restricted Euler, right?
Yes, exactly.
It's exactly the restricted
Yes.
Euler. Okay. So have you checked for other closures for the pressure Hessian?
No.
That might influence the results, right?
Yes.
Yes, back.
I think these guys were first and then...
Sorry.
Okay.
I always think it's useful for this problem to think in terms of the Berger's vortex.
Yes.
And we often think that, well, obviously it goes in the direction of the maximum
Yes.
strain. However, the vortex itself in the plane has shear
Yes.
with principal axes
Right.
in that plane. And if it's a strong vortex, that
Right.
maximum is there. So the axis aligned with the vortex is the intermediate rate of strain.
Okay. I see.
Is that not the simplest physical interpretation?
Yes, I think so. Yes, I think so. But in that kind of picture, always start with the external strain given.
Yeah.
But in this model, we tend to not to give the external strain. Yeah, but it's just a pretend.
Yeah.
Maybe the same. So anyway, fix the point tells you basically the same structure.
All right, so in an effort to maybe to bridge the statistical and the dynamical, have
Yes.
you thought about trying to investigate how robust the meander is against some appropriately chosen noise?
Okay, but
which would seem
right.
to be relevant here.
Right, but if you believe in the model, we need to follow the Lagrangian trajectories.
Right.
And the Lagrangian evolution of pressure Hessian and so on is, I'm sure this is not as simple as we assume in deriving the model.
But do you have any sense of how robust this state is?
I just hope it's robust, but I'm not, for the extreme cases like very high strain field, high strain points, or very high vortex stretched regions, things may be very different from the average picture. So there are two extremes. One average structure, and there's maybe extreme events, and maybe those two swing together. And in that sense, the robustness may not be expected. Am I answering your question?
Somewhat, yeah.
Yeah, we haven't tried to study those robustness with the DNS data.
So in your model, you put a lot of weight on the trajectory, which kind of came near theta equals naught.
Yes.
But you could get all the statistics out of your model, couldn't you, very easily. Do they agree with the statistics of the full system?
Right, but actually in this simulation, we didn't consider the exchange of the eigenvalues and eigendirections. In some cases, the lambda 1 and lambda 2 are getting very close, and that exchange occurs this region, basically. So we need to clean those exchange of the lambda and EIs, then maybe we can do the statistics.
Okay, any more questions? Yes, please.
I have a question. Your model of this problem is in closed system or open system? How I found you didn't mention the boundary condition.
Okay, so this is we assume the simulation, we assume the periodic boundary. And for this model, for this kind of modeling, we assume the turbulent flow is far away from the boundary, and the velocity field is homogeneous and isotropic.
Do you think the boundary condition may impact on the
okay, so if you are very interested in, for example, the flow close to the wall boundary, then those alignment properties is very different, completely different. So this is an alignment in the homogeneous isotropic condition.
Okay, thank you.